we completed the application of concepts of system of particles and application of Newton's second law to a system of particles for variable mass systems like the rocket in outer space and a conveyor belt with mass increasing on it, etc. So we have mostly finished system of particles, everything. Now today's lecture we'll wind up system of particles with some additional questions and problem solving techniques, okay, so that we can then be in a position to start with the next topic, which will be rotational mechanics. So let's begin. So we'll start with a couple of applications of variable mass type of systems only, and then we will also see some more example or practice questions with collisions and impulse and that kind of concept, okay, before we finally move on to rotation after that. Okay, now an interesting type of application of variable mass system, something like this. Suppose we have a chain which is being held vertically, initially being held at rest, with one end of the chain just about in contact with the ground below. And then what we do is we release the chain from this position, and the chain sort of lumps up at the ground where it falls. Okay. Now, assuming that as the beads of the chain hit the ground, they come to rest immediately. So they make inelastic impacts with the surface of the horizontal surface. Okay. We have to find the speed of the moving part of the chain, that is the vertical part of the chain, as a function of how much of the chain has lumped upon the ground. And we have to also find the contact force, that is the normal reaction contact force between the ground and the chain, as a function of that distance or displacement or whatever. Okay, so let me explain the question fully. So this is a chain of length L, which is initially at rest in this position. It's released from this position at time t equal to 0. Okay. So this end of the chain is, let's say, A, the other end of the chain is B. So a uniform chain of mass m and length L is released from rest from a vertical position as shown, with its lower end just in contact so it's just about in contact with a horizontal surface. Now, assuming the chain's links do not bounce, that means they come to contact. They come to rest the moment they come to contact with the ground or with the horizontal surface, which is about the inelastic impact I was telling you about. So, assuming that the chain's links do not bounce, as they come in contact with the surface, okay. And also the chain does not bunch up, but rather its mass spreads uniformly on the ground. So with these two assumptions in place, we have to find the speed of the top end A and the normal contact force at the surface as functions of x, that is the displacement of the point A. So just take down the language of the question or understand it carefully, then we'll discuss how to solve this. Okay, so let's understand the first aspect of this question. How to find out the speed of the point A, the top end of the chain, as it is displaced through a distance x. So the first thing we have to understand here is that we cannot apply conservation of energy in this type of situation. And the reason for that is very simple, that the collisions that each link is making with the floor as it comes in contact, the type of collision is inelastic, so it absorbs energy. The non-conservative collision forces or collision impulses which cause mechanical energy to get dissipated into other forms of energy. So conservation of energy will not be applicable. So we compare the initial instant with after some time, a situation where something like this has happened. Some part of the chain has come to rest on the ground, whereas the end A is now, this section is moving at a speed V. So this distance from here to here, this is the displacement, downward direction, distance this much of the point A. So we have to find this speed of A as a function of X. So first and foremost, as I told you, that mechanical energy, that is kinetic energy plus gravitational potential energy, will not be conserved. As the collisions of the links of the chain with the floor or with the horizontal surface are inelastic collisions. In fact, they are E equal to 0 type inelastic collisions because they don't bounce. Okay, and therefore energy dissipation occurs. That's the first point to understand. The second point to understand is that before coming in contact with the ground, any link while it is falling through air, it is not in contact with any other link, so it is in free fall. Okay. So as a link displaces vertically before coming in contact with the ground, it is not in contact with its neighboring links. Okay. It is therefore in free fall. Okay. So therefore we can see that as the chain falls through a distance of x, okay, the top end A of the chain falls through a distance x. All the links which are in free fall, they have been in free fall for a distance of x. So we'll apply kinematics for them. So therefore, as the chain falls through x, so during that time also a portion x of it comes in contact with the surface and comes to rest on it. Okay. But the other thing is, as it falls through a distance x, each link in the vertical section has been in free fall. It's had a downward acceleration equal to g, starting from rest. Okay, for a displacement of x. Hence, it's very simple to understand that v will be equal to root 2 gx, just using kinematics. Okay, so this becomes the solution of the first part. In fact, the speed of the vertical part of the chain at an instant when the vertical displacement of the point A is x. So just make a quick note of this, then we'll move on to the second part. So the other thing you can also see here is that now in the second part, like as the point A has come down by distance x, the portion of the chain which is above ground, which is vertical, is of length L minus x, whereas an equivalent portion of length x has come in contact with the ground. So at any instant, a particular link of the chain is hitting the ground, and the moment it is hitting the ground, a certain amount of momentum as well as kinetic energy is absorbed in the impact. So non-conservative situation is happening. The collision impulses are non-conservative because they are absorbing or they are dissipating kinetic energy. And of course, they are absorbing momentum. Okay, now let's come to the second part. We want to find the contact force. Okay, at an instant like this, when the vertical portion has displaced through a distance x. So anybody about how we will calculate the contact force? Okay, so about the contact force, what we have to understand is that the normal contact force with the ground is absorbing the momentum of the links of the chain as they are coming and hitting with the ground. Plus, they are of course balancing the weight of those links which are already on the ground. Okay, so it is not just equal to the weight of the section which is on the ground. It is also equal to the rate of change of momentum. Okay, so if you think of the mass of the chain which is on the ground, it's a variable mass. It's not constant. So that's why I said this is an application of variable mass system in that sense. Suppose we look at the situation at an instant of time t. A little more space here, just a moment. Yeah, so suppose this is the situation at that intermediate time t, which I had drawn in the second diagram earlier. So there's a certain amount of mass spread out on the ground here, and certain amount of mass which is in free fall, which is having an instantaneous velocity of root 2 gx. Okay, so this section is of length L minus x. Okay. Now this is suppose at time t. Now what's happening at a very small time later at t plus dt? Slightly larger portion is now on the ground and slightly smaller portion is now above the ground. Okay. So during this time dt, this has come down through a small displacement dx. So this portion has become L minus x minus dx. So if I look at the free body diagram of this portion which is on the ground, so at time t equal to t, this is a mass of m by L into dx. Oh, sorry, m by L into x. It has this much mass. Let's write this as capital M. Capital M is the total mass of the chain. And L is the length. Okay. So M by L is basically the lambda of the chain. You can also write it like this, that the portion on the ground at this point of time is lambda x. Okay. And also the portion above it is moving with a velocity v. Okay. Now, what are the forces acting on this portion? There is normal reaction and there is small mg into x. Okay. Small mg. Now, if I look at this and moment later, that is at t equal to t plus delta t or t plus dt, the portion on the ground, its mass has just increased a little bit. Its mass has become m plus dm. That is lambda into x plus dx type of thing. Okay. So what has happened, that dm mass which has got added here, it was above ground. Okay. So the change in momentum from here to here, the change in momentum of that portion on the ground is dm into v upwards. Because what was happening is that this dm was traveling down with the speed v. Okay, at t equal to t, and now that dm is on the ground, it's at rest. So the change in momentum of the system from here to here of the total mass m plus dm, this total mass on the ground at this time what is the change in momentum for it? It is the final momentum minus the initial momentum. So the initial momentum still had this particle of mass dm, or this small section of the chain of mass dm having a downward velocity v. So the initial momentum was dm into v downwards, and after that instant dt, that momentum has become zero. So the change in momentum is this much. Okay, this is the change in momentum. Okay, so now we'll apply impulse momentum theorem. So impulse equals to change in momentum. Since the momentum is changing in the upward direction, we have to calculate impulse in the upward direction. So n minus mg is the net force. So that into time dt is the net impulse. This is the net impulse during that time. And this is equal to the change in momentum. So that should be equal to Tm into V. So n becomes dm by dt into V plus mg. So this is an important concept over here. The normal reaction that is acting on the ground, it is equal to the rate of change of momentum being absorbed, because part of the chain is coming and hitting the ground, plus the weight of the portion which is already at rest on the ground. That's why I told you in the beginning that it's going to be more than the weight of the section which is on the ground. Now, how we'll calculate dm by dt, will come to that. But first, note down this section. This is important. So hope you're following this. Please let me know if there's any doubt.
Done, sir.
Okay, understood this part now?
Yes, sir, like getting it.
Okay, so now how we will calculate this dm by dt? Okay. Dm is the mass which adds to the pile on the ground, okay, in time dt, right? So the section of the chain which is on the ground, okay, so dm is the mass added to the portion on the ground from t to t plus dt. Okay. So at t equal to t, the length of the portion on the ground was x, but at t plus dt, the length became x plus dx. Therefore, how much mass was added? Lambda into dx. Okay. So between this time and this time, how much mass is getting added? That's lambda dx. Okay. This mass. So therefore, this term dm by dt is equal to lambda dx by dt, which is nothing but lambda into v, because v is the rate at which the chain is falling to the ground. So hence, this term dm by dt into v, this actually becomes lambda v square. And just now we had seen that v was equal to root 2 gx. So therefore, that term dm by dt into v, it becomes lambda into 2 gx, which is total mass per unit length. Okay, into 2 gx, like this. So therefore, coming back to the normal reaction was dm by dt into v plus the weight of the portion which is on the ground. Now in this also, this is lambda x or m by L into x. M is equal to that much. So this first part dm by dt into v becomes lambda or m by L into 2gx. And the second part, the weight of the portion on the ground, that becomes lambda or m by L into x into g. So the total normal reaction you can see becomes 3 times mgx by L. So it is in fact 3 times the weight of the portion on the ground. You can see that mg is m by L into gx, but normal reaction is 3 times this. Okay. That is because normal reaction is the sum of these two things, the rate of change of momentum or the rate at which momentum is being absorbed, and that is dominating in fact over small mg. Okay, so this is the rate of absorption of momentum of links hitting the surface, plus this is the weight of the portion which is on the surface. And together their sum is in fact becoming 3 times small mg or 3 times capital Mg by L into x. Okay. So this is an important type of application of variable mass system and impulse momentum theorem. There are a few variations of this also at JEE Advanced level. Okay. And as you do the practice exercises from your, especially from your module, in HC Verma, you will not find these type of questions too much. The questions are more concentrating on the collision type of situation and conservation of linear momentum type situation. There isn't that much variety in the questions for variable mass system. But in your module, you'll find some variations of this. You can try those out and you'll be able to apply the concept as long as you're clear what we're doing over here. Okay. So just make sure you understand the steps over here. Let me know if there's any doubt. Okay, so first make sure you're clear with this part, and we'll come to the last portion. So the answer is here itself, 3 mgx by L. This is the contact force as a function of x.
This type of question comes for JEE Advanced.
Yeah, it's more for JEE Advanced compared to JEE Mains. JEE Mains, the variable mass type of question will be the direct standard application formula type question, like you have for the rocket propulsion system we discussed last time.
Sir,
Yes.
sir, could you just go up?
Yeah, sure. This part?
Sir, could you just yes, sir, could you just re-explain that impulse part where you have written that n minus mg times dt? That one part.
So
Could you
see,
just
what is our impulse momentum theorem in general? That in any duration of time, if the net impulse acting is J, that should be equal to the change in momentum, right? During that time for any system. Okay. This equation is clear, no? This is the impulse momentum system, impulse momentum theorem for a system.
Yes, sir.
Okay, so if we now talk about a small time dt, during that small time dt, then net impulse acting is the differential impulse. Okay, so that should be equal to the differential change in momentum. So left hand side of your equation, the differential impulse will become what? Net force into time, and right hand side it is the change in momentum dp. Okay, now apply this to this system over here. So what's happening? If you look at this system at time t, there is some mass small m on the ground, and there is this kind of mass which is falling. So the dm mass which is going to combine with the mass on the ground, that is having a downward velocity of v. So the initial momentum of the system we can say is dmv downwards. Forget about the parts which is above this, because that's not going to hit the ground yet. Now instant later at dt, this dm which was above the ground coming down at speed v, that is also come and hit the ground and come to rest. So the momentum has become zero. So between here and here, what is the change in momentum? The change in momentum is that particle of mass dm coming to rest. So its momentum has got absorbed by the ground. So it's got an upward change in momentum. It's clear now?
Yes, sir.
Okay, now come to the left hand side of the equation. Now we'll convert this to scalar form because it's one dimensional. So I'm taking the upward direction as positive. So I have to calculate the net force in the upward direction. So this free body diagram, these are the two forces that are acting on this portion: normal reaction upwards and mg downwards. So the net force upwards is how much? N minus mg. So that net force into time dt, this only is our impulse. This is our impulse during that small time dt, and it's absorbing the momentum of this incoming particle dm into v. So this is our change in momentum. Clear now?
Yes, sir. Got it.
Got it now? So this is a little tricky, this part. And then the rest becomes just mathematics. Once you're clear with this equation, this one here, okay. Rather this equation, from here, the rest of it is just you're transferring the terms, then you're interpreting what dm by dt is.
Sir, could you just go down?
Yes. Okay, so you have understood up to this step, right? This.
Yes, sir. Now got it.
Okay. So now basically we have to solve this dm by dt term. So dm by dt is the rate at which mass is hitting the ground. So that will become lambda into dx by dt. That is the mass per unit length into the rate at which the length of the chain is hitting the ground. So that's what we're seeing here. That dm mass was added to the portion on the ground from t to t plus dt. So that dm is lambda dx. So because dm is lambda dx, therefore dm by dt becomes lambda into v finally. And accordingly, dm by dt into v becomes this term that we want to calculate. That becomes this. Okay, so this is done now. This clear?
Yes, sir.
Okay. Okay, so hope all of you understood how we get the total normal reaction at any instant. That is equal to 3 mg L by X, like this. Of course, this is true till X becomes equal to L. Once the entire chain comes and rests on the ground, then there is no more absorption of momentum happening. So then that entire mass capital M has come to rest. So then the normal reaction will stabilize to the value capital Mg. So as the chain is falling, also you can see the normal reaction is decreasing because X is decreasing. And as X becomes equal to L, it increases to the maximum value 3 mg for an instant. And the moment later, this term is gone. This dm by dt into v term is gone. So we are just left with the total weight of the chain on the ground, which is capital Mg. So there's a sudden change in normal reaction when the last link of the chain has hit the ground. As it is hitting, it's 3 times the total weight of the chain. But as that collision is completed, it suddenly reduces from 3 times the total weight to just the weight, capital Mg. Okay. So very interesting type of situation here. Okay, now let's move on to another application of variable mass system, which is a variation of the rocket propulsion system. So we will look at the rocket system during takeoff from the ground. At Earth's surface. Okay, so now the difference is that along with the thrust and all that, there is also Earth's gravitational field acting on the rocket. So that has to be taken into account when we are calculating the instantaneous acceleration. So let's say this is the mass of the rocket at time t. So moment later, it has ejected out a certain amount of fuel. So its mass has become a little bit lesser. Because it has thrown out dm amount of mass in the downward direction with a velocity of, let's say, u relative minus that same concept that we discussed. Okay. So this is what is happening at t equal to t plus dt. So the mass of the rocket has become dm minus m because dm amount of mass has been removed. And the rocket's own speed has increased from v to v plus dt. Okay. But when we look at this whole thing as a system, going from here to here, continuously there's the weight or the gravitational pull of the Earth which is acting on it. So that gravitational pull of the Earth is mg. Okay. So when we apply this concept now, that net external impulse is equal to change in momentum for the system. So we can see that going from here to here, taking the upward direction as positive, you can see that the impulse acting is because of gravity. So that will be minus mg into dt. This is the net external impulse. So that should be equal to the change in momentum. Now the change in momentum will be the momentum, which is m minus dm going with a velocity of v plus dv upwards. Okay. Plus the dm mass which is it has rejected or which is ejected downwards, but it's coming down with the speed v1. So it will come with a minus sign. So this is the final momentum in the upper picture minus the initial momentum in the lower picture, which was mv. Okay. So this is the change in momentum. So it's the same as the expression we had earlier, but this expression was equal to 0 because the rate of change of momentum was 0. But here it is equal to the impulse. So now we can see that this equation gives us this, that minus mg into dt. When we open this bracket, we have again all those kind of terms. Okay. Minus dm into v, okay, minus dm into dv, okay, minus dm into this term. V1 is now u relative minus v minus mv. So we'll see all these terms now cancel. This term and this term cancels out. Okay. Then this term and this term here will cancel out. Okay. And this term is negligible because it is a product of two differential terms. So we are left with this now. Okay. So we can see that mg is equal to dm by dt into v. Wait a minute, I made some mistake here. Sorry, this term doesn't cancel. It is the other term that cancels. If this term remains, is this term that will cancel. This minus dm into v and this plus dm into v here will cancel. So the term that we are left with here is this one, mdv, okay, minus dm into. So absorbing the minus sign, this will become dm by dt into u relative minus m dv by dt. So it's like instantaneous mass into instantaneous acceleration is equal to this term, the thrust force that we had discussed about last time, but minus mg, because this time there's the additional force also. So the gravitational force, which is going against your acceleration. So this is like your instantaneous mass into acceleration is the thrust provided by the rocket engines minus the weight of the rocket, because you still have to overcome the weight of the rocket at the Earth's surface. Okay, where we understand that F thrust is equal to the burn rate dm by dt into the relative speed with which this is going. So this becomes a variation of the rocket propulsion system that we had seen in outer space. In outer space, that mg term was missing. So it was just F thrust is equal to m into dv by dt. But now there is also that minus mg, because the thrust is acting against gravity in the opposite direction to give it lift off. So actually the proper term for this is lift off, not take off. Okay, so is this clear, people? All right, now let's move on to another type of situation.
Sir, could you just go back?
Okay, you want to finish writing that down? Yes.
Yes, only that equation part which you have written on the right hand.
It's okay. The concept is clear now in this question.
Yes, sir. That how is it happening?
Done?
Yes, sir.
Okay. Okay, now next type of question is like this, that suppose we have this situation like, this is a carom coin on a smooth carom board surface. Two identical such discs or carom coins. Okay. Now just think as if they are connected together by a thread. So they are joined together by a thread, and So, this is the top view of the carom board table. Okay, so the actual situation is more like this, that this is a smooth horizontal surface on which these two are lying. Okay. So this is a smooth surface. Now they're joined together by a thread which is initially slacked like this. Okay. So A and B are identical disks or particles, you can say, joined together by a thread of length L, but the distance between them right now, this distance from here to here, this is only right now 0.6 L, where L is the length of the thread. So this is a thread which is loose or slack right now, but of length L. Now what we do is we set off this one B with an initial velocity in this direction, perpendicular to the line joining the two of them. Okay. So A and B are identical disks of mass M on a smooth horizontal surface. At a distance of 0.6 L. Okay. Assume that the radii of the disc is negligible compared to this length L. Okay. And they are connected by a thread of length L. Now B is given an initial velocity V naught, okay, perpendicular to the line AB. So find the velocity of A and the velocity of B at the moment just after the thread becomes taut. Okay, so what you will see is that B will just continue in uniform motion for a little bit of time, but at a certain instant, the string suddenly tightens. So that's what we mean by saying it becomes taut. So the moment that string tightens, okay, it pulls A with it, and it also pulls back on B. So B's momentum changes, A's momentum changes. Okay, and as a result of that, the velocity of A and B is going to be something different than the initial picture. The initial picture, the velocity of A is 0, and the velocity of B is V naught along this direction. Okay, so we have to find the velocity of A and B at the moment just after the thread becomes taut. Okay, so I'll just give you a minute to work out the geometry of this, that what is the position between A and B just at the moment when the string becomes taut, okay, to understand the question, and then we will discuss about what we have to apply in the question. Okay, obviously A plus B as a system, we will apply momentum conservation, but we cannot apply conservation of energy here because the string is not an elastic string. So as the string jerks, as it becomes taut, it kind of jerks. So that jerking force or that impulse that acts through the tension of the string is like an inelastic impact impulse. It dissipates energy. So momentum conservation is the only thing we can go by for the system A plus B over here to solve it completely. So just note down the question and try this out.
Sir,
Yes.
so in the right part of the rough diagram, what did you write at? Which is repeating
Sorry,
that.
come again, Bhargav, in the.
Sir, on the right hand part where you have written something like where the two masses A and B
it's-
are on the surface.
It's a smooth surface, madam.
Okay.
It's a smooth horizontal surface. I'll just rewrite that. Okay. Basically, if you look at the three-dimensional view of this, okay, this is, imagine they're on a horizontal tabletop or something. So this is a smooth surface. Okay. And on this, we have placed the two discs or carom coins or whatever like this. And they are connected by slack string. Okay. And then we set off B in this direction. Okay, along the surface only, but perpendicular to the line joining it. So gravity is going into that plane. So this is like the top view of a smooth horizontal surface. So here gravity is like this. Okay, so first of all, just work out the angle and the geometry at the instant when the string is about to become tight. The string is just about becoming taut or tight when the distance between A and B's endpoints, where the thread is attached, that changes from 0.6 L to L, because L is the length of the string. Okay, so let's look at this situation in a bit more detail now. So this was the initial state. So the thread is slack here. And B has a velocity along this line downwards. So right now the distance between these two is 0.6 L. Mind you, it's not like the center to center distance, but it's like the distance from edge to edge. Okay. Now, what happens is from this point onwards, B will continue down without any impulse acting on it because the thread is taut till a certain amount of time. So let's assume that just before the thread is going to tighten, this is the situation. So B has traveled through a certain displacement without it being affected by any force because the thread has not yet become taut. So it's still having a downward velocity V naught. But now the thread is about to become taut. It's about to become tight. So it's kind of like stretched out now like this. So the radius is negligible, so we can just, so you can see that this being 0.6 L, you can see that this angle here, this theta is, you can see it's sine inverse of 0.6 or 3/5, so it's 37 degrees. Okay. Now the thread just becomes taut. So as the thread, so this is, the situation of momentum just before the thread becomes taut. Okay. Now from here onwards, as the thread is becoming taut, it's going to develop like a jerk, like there'll be a sharp impulse for a certain amount of time acting till the momentum of these two changes. So the string will apply an impulse like this on this as it becomes taut. So as the thread tightens, an impulse J, like a jerk, acts through it on each of bodies A and B. Okay. And as a result of this jerk, now we'll see that next instant. So all this is happening in a very short duration of time, from this diagram to this diagram to the next one. So all this is happening pretty fast. And once the string has applied this kind of jerk, we will see that the system's momentum or A and B's individual momenta have changed to something like this now. A will develop a momentum along the direction in which it experiences an impulse. So let's say this becomes VA because it was at rest before. A was at rest in this diagram, it experienced an impulse in this direction. So its final momentum will have to be in the direction of the impulse. Okay. Whereas B, if you think about it, B had a momentum in this direction, MV0. Okay. And then it experienced an impulse in this sort of direction. So final momentum has to be initial momentum plus impulse. So its final velocity is, let's say, in some sort of direction like this. So B's velocity is, let us say, in some sort of direction like this. So we have to compare the first and third diagram, or rather the second and fourth diagram that I've drawn over here. We have to compare these two to find out VA and VB from the value of V0 over here. Okay. So this is just after the thread is taut. Okay. So if you compare these diagrams just before and just after, you can see that on the system there is no net external force. Okay. The impulse is internal. So taking A plus B as a system, the net external impulse is 0. Okay. So there is conservation of momentum. So initial momentum of A was 0 and B was mv0. This should be equal to final momentum of A plus final momentum of B. So we have to convert this into equations. Okay, but still, this will still leave us with one extra equation. I mean, one extra variable, because we know VA in terms of both magnitude and VA we know in terms of directions. We just need the magnitude of VA, because we know that angle theta is 37 degrees, but VB we don't know the direction of. So we need like the direction as well as magnitude. So we have three variables that we require to solve. One is the magnitude of VA, and the other is the magnitude of VB, and also the direction of VB. So we need three equations. Now this vector relation that we have over here, momentum conservation, is going to give us two component equations, but a third equation will also be required. So the third equation has to come from an additional concept, and the concept for that is that the thread is of fixed length. So as A and B are moving, okay, the distance between A and B should remain fixed after the thread becomes taut. So in fact, we will see that the direction of B's velocity after impact is going to be more like something like this. Or something like this. So conservation of momentum, when we apply this now, that will give us two equations, two individual component equations. But we will need a third equation also, because we don't know the direction in which this VB is there. Okay, so let's look at these two diagrams more closely and understand how we can apply momentum conservation by breaking into components. Okay, so for momentum conservation, the first option that we have is that we can just take the direction of V0 as our y-axis, and the perpendicular direction to that as our x-axis. Okay. So we can do like this. We can take this as our y-axis and this as our x-axis. So in this diagram, we can see that this angle is theta. Okay, and this we will have to break into components. So we'll have to take this as some x component. Sorry, that as some y component and this some as some x component. So when we write this in component form, we can see that before impact.
Sir, but why are to break in component form?
How else we will do conservation of momentum? Tell me. We have to apply momentum conservation, no?
Yes, sir.
So you can see the vectors are in different directions. No? So we have to. So when we are doing this equation, no, that mv0 is equal to mva plus mvb, conservation of momentum. Okay. So we have got this equation because the masses are same, but this is a two-dimensional vector equation. No? So to solve it, we have to convert into components. Okay.
Yes, sir. Understood.
So before impact, A's velocity was 0 and B's velocity, if we write as UB, we can see it is V0 J cap, the way we have taken our y-axis. Okay. Whereas after impact, you can see that A is velocity. This angle is theta. So it will have a component of V naught sine theta along the x-axis plus V naught cos theta along the y-axis, because theta is the angle with the y-axis, not with the x-axis. And theta is equal to 37. We had seen that before. So this is equal to 3 by 5 V naught I cap plus 4 by 5 V naught J cap. That is A's velocity. Whereas what about B's velocity? B's velocity, we don't know this angle. Okay. So we have to take both the components as unknown. So we are just taking it as minus Bx I cap plus By J cap. Minus because it's along the negative x direction. So now when we apply this conservation of momentum equation, we can see that we'll get two individual equations, one along the x-axis, one along the y-axis. Okay. So we break this into, along the x-axis, we have 0 is the initial momentum. So that is equal to 3 by 5 V naught for A minus Bx for B. Okay, so that's our first equation. And along the y-axis, the initial momentum is V naught, and the final is the sum of these two. So that is 4 by 5 V naught plus Vy. Okay. So the first equation, in fact, tells us that Vx is equal to 3 by 5 V naught. But the second equation doesn't give us a direct answer like this yet. Oh, just a minute. This is not V naught. No? This is Va. That's what I was thinking. Too many. This is also an unknown. No? The magnitude of this one's velocity is not known. So just a moment. Yeah. So the magnitude is some unknown. Okay, but theta is known. So this is 3 by 5 Va plus 4 by 5 Va. So in this, Va is unknown. Okay, but theta is 37. And in this, Vp's components, that is Vx and Vy, are both unknown. Okay, so that's why we got this. Okay, so the first equation along the x-axis, I'll have 3 by 5 Va minus Vx. And along the y-axis, I'll have 4 by 5 Va plus Vy. So these are my first two equations. So the first equation is also giving me this relation that Vx is equal to 0.6 times Va. But the second equation has more number of variables. Va and Vy are both unknowns. Okay. So you can see that the variables for us are Va, Vx and Vy. And so far we have only two equations from momentum conservation. So note this down and think carefully and tell me how I'll get a third equation. I need a third equation to solve this now. So what about the third equation? What concept that will come from? Okay, so
Sir,
let's
can
discuss
you
how.
scroll up?
Scroll up. Okay. What about the third equation? Have you thought about how that's going to come?
No, sir.
Okay, so I'll tell you, see what's happening. The thread length from this time onwards, now when this thread becomes taut, from after this instant onwards, that is from this third diagram onwards, the thread length is constant. The distance between A and B is fixed. Okay, so that should give us a relation. The velocity of A and B should have such a relationship that their relative velocity of approach is how much? 0. Their approach or separation velocity should be 0 because the distance between them should be neither increasing nor decreasing. Understood this now?
Yes, sir.
Okay, so that will also give us another equation. Now, that equation is going to be a little complicated because we have written VB in terms of X and Y components, whereas actually we want to trace the approach or separation velocity. So that is along this line, along the line EB. So we'll come to that. First, make sure you're clear with the two equations that we've generated so far from momentum conservation.
Sir, so we have to assume VB's velocity, no?
We
In
have to
that
assume?
direction. Sir, VB's velocity in that direction.
Yes, we have to find the net velocity of VB along the line AB. Okay, so these two equations are clear to all of you, right?
Yes, sir.
Now let's come back to this. So what's happening just after the string has become taut? Okay, at that moment, what is happening is A is having a velocity directly towards B. Okay, but B is having one component of velocity like this, and one component of velocity like this, such that you can also see that with respect to this line AB, this angle is theta. So if I also draw perpendicular over here, you'll see this angle is theta, correct?
Yes, sir.
The angles are correct now? Okay. So now you can see that we want to calculate the approach velocity of A towards B, the net approach velocity, the relative velocity of approach. Okay. Or the relative velocity of separation of A with respect to B or B with respect to A, whatever. Whichever of the two we consider, this has to be 0. Now, why? Because the thread length is fixed. So the distance between A and B is fixed. Okay, so whichever of these two quantities we calculate, the relative approach velocity of A towards B or the relative separation velocity of B from A, that should be 0. So let's calculate this now. Okay, so the relative approach velocity of A towards B is 0. Now see, A directly has a velocity of VA towards B. So that is giving it an approach. Okay, now B has this component Vx in this direction. So that Vx in this direction has a component towards A of how much? Vx cos theta.
Yes.
And there is also this third component Vy. So that is away from A. So that is giving it a negative term of Vy. Sorry, this one is sine theta. Because the angle with the thread is 90 minus theta. No? This angle is 90 minus theta. So
Yes.
So this is, and this is minus Vy cos theta. This should be 0. So how we think of this equation that we got, think of it like superposition. Okay, suppose B was at rest and only A was moving towards B. then the approach velocity would have been directly VA. Okay. Now think that VA is not there, Vy is not there, but only V is going with the velocity Vx. Then what would be the relative approach velocity? It would be B's component towards A. So that would be Vx sine theta. Okay. And now think these two are not there. Va is not there and Vx is not there. Only Vy is there. So Vy is having a component away from A along the line AB. So that is giving it a separation. So in terms of approach, it is minus Vy cos theta. Now superimpose the three things, that A is also moving with VA. B is having an X component Vx in this direction. So that is bringing it closer to A by a factor of Vx sine theta. It is having a Y component in this direction. So it's separating it at the rate of Vy cos theta. So that is equal to 0. So ultimately we are getting this equation, that VA plus 3 by 5 Vx minus 4 by 5 Vy is equal to 0. And that is our third equation. Okay, because theta over here we know is 37 degrees. Now we will solve the three equations for the three unknowns, VA, Vx and Vy. And from that we will know the velocities VA and Vb as vector quantities in terms of our I cap and J cap. Where for us the J cap is downwards, okay, and the I cap is like this. This is the system of axis vector.
So can you zoom out a little bit?
Yeah. Is it clear now?
Yes, sir.
Now, the momentum conservation part you've seen before also. This is the next thing that you have to see, that this approach or separation velocity should be 0 because the thread length is fixed. So this situation, so once the thread is taut, from that point onwards, this should happen. Approach or separation velocity should be 0 as they move. Okay, so let's also look at solving the equations now. So the first equation was telling us that Vx is equal to 0.6 VA. Okay. Second equation is telling us that 0.8 VA plus Vy is equal to V naught. Okay. And the third equation now is telling us that VA plus 0.6 Vx plus 0.8 Vy is equal to 0. Okay. So what we can do is we can first try to find out VA in terms of V naught. So we can substitute Vx from equation 1 into equation 3. So substitute this. Okay. So that will give us Vy in terms of VA. So we will then substitute this Vy in the second equation. So that will give us VA in terms of V naught. And then we can substitute that in the two equations and we'll get Vx and Vy also. Remember, V naught is the known quantity and Vx, Vy and Va are the unknown quantities. Okay, so let's do this substitution. So equation 3, it will become Va plus 0.6 Va, Vx. Now Vx is how much? It is 0.6 Va. Okay, plus 0.8 Vy is equal to 0. So this will tell us that Vy There's a minus sign. That's what I thought. Can't get Vy as a negative quantity. Yeah, there's a minus sign there. So Vy will come out to be how much? 1.36 divided by 0.8 times V. .7 in fact, isn't it? Then we will substitute this back in the second equation. So we'll get our required thing that 0.8 VA plus 1.7 VA is equal to V0. We get VA as V0 upon 2.5 or 2 by 5 V0. And from that we'll get Vx as 0.6 times this. So 3 by 5 times this. So 6 by 25 V0. And Vb as 1.7 times Va. So that is 3.4 by 5. So finally, we will get E's velocity as a vector quantity as all right, people. So hope this is clear. Just minimize this a little so you can.
Done, sir.
Okay, done now. Understood this question fully?
Yes, sir.
Okay, so this is a lengthy and tricky type of application of concept of center of mass and impulse and all that. but again important from the JEE Advanced point of view. So let's look at our final example for today. Now this is this kind of situation. So we have a triangular wedge like this. It's sitting on a frictionless surface. So this is of mass m. These angles are theta. This is a smooth surface. Okay. Now a particle of mass small m, it is dropped from this position. Okay. In fact, a little bit here. Yeah. So let's say it's dropped from this position, so that it makes an impact at this point on the surface. And what the question says is immediately after the impact, the particle has a horizontal velocity. So a particle of mass small m is dropped from height h. Let's say that height is 20 meters onto the surface of the wedge, okay, of mass capital M, such that mass capital M is, let us say, 5 times the mass of the particle. Okay. And also this angle theta, this angle theta is 53 degrees. Now just after impact, the particle's velocity let's say v1 is horizontal. Okay. So if the wedge's velocity is v2, then find v1 and v2, I mean magnitudes of v1 and v2. Okay. And secondly, find the coefficient of restitution for this particular impact. Okay. So just try out this question. We'll discuss. Good evening, sir. Sorry. Yeah. Extremely sorry. I was trying to get back to the email of the network. I'm sorry for delaying so much. Actually, it's been a little difficult for us to organize things with the way the pandemic is going and the uncertainty.
Sir, your mic is on.
Parents and the school boards and all that also. Yeah. So, sir, the problem is that right now we are not able to launch a non-integrated full-fledged batch for medical students or new students for our knowledge center as such. So there are a couple of options that I can tell you. So first of all, sir, we
and the timings will be the morning time, right, for the online class. So what will happen is, yes, we will have like if the pandemic is happening, because of that online classes are happening, we do have an online batch for the afternoon and evening hours for medical entrance. But that is like a pan Mumbai kind of group, because they are having limited number of admissions and non-integrated, especially for medical. So like there are 5 students from Nerul, there are about 12 students from Bhattacharya, 3 students from Untitled. Currently they're put together in a batch. In Thane, you're not having enough number of students, and more importantly, you're not having the type of students for medical entrance non-integrated. But ISTA really under performance, and I think I've spoken to her also a couple of times for that. I know that kind of I don't have that kind of full-fledged action. So one thing I can offer you that in fact this is what we've been discussing also, but unfortunately because the pandemic also is work our group like we are 30% understaffed right now, because many people either they're down with COVID themselves or family. The important decision making is also getting a little delayed. But today I have talked to some of my senior partners and they come to this consensus that we will be having a system this time because of the pandemic, where there will be for non-integrated students a sort of hybrid batch, where the lectures will be conducted on the online model. There will be like 3 sessions in a week for each of the subjects for which they can come to the center for solving their technical doubts. Okay, so for example, yes, yes. So yes, so for example, yes. So basically, let me try and give you the picture. So for example, we have like a whole pool of students from BRC who are not able to attend our classes because our classes were and many of them are unable to travel because of the pandemic even later. So they will be attending online from them, from Chembur. Then we have some students who are in the non-integrated program from Nerul, Arthur, and very Thane, etc. So they all be attending as a common batch of 30 students online for the regular classes of biology, physics, and for the regular lectures. However, once the pandemic is over, or even before we can conduct classes, after you to open our center again for the students, we will be calling the same students in small batches of 4 to 5 students at the center. Whether teachers will be available for the doubts. So for example, in Thane here, the teachers who will be teaching them physics and chemistry will be the same who are teaching the engineering batches. They are going to be there full time anyway. So there will be extreme flexibility because they will be there over practically. So the down session for staff because teachers and other students and not integrated over are there. I have like right now 2 students, right? Apart from this, they will get to attend physics chemistry quite flexible. Whereas the biology subject experts, you don't have the integrated, non-integrated batch of time. They will be coming once a week for discussion of their topics. So this is the kind of hybrid model, and we are still working it out on paper exactly how it is distributed. But since it will be a hybrid model, it will be quite cost effective also. And I can tell you that the fee structure that I told you 1.5, 1.9 lakhs approximately, that was for the 2-year integrated program with the number of hours. With a hybrid model like that, I can guarantee that they will come down by quite a large percentage. But at the same time, I guarantee that once you finish the regular lectures, you will have very good for those students because there are good students from DRC, particularly from level. And because the online batch will also only 30 students, so it will be interactive. You can ask doubts and all that. And plus, I will guarantee that the senior teachers will be there every week for the discussion of doubts and physics chemistry. We will be tracking the performance like a regular batch. The only difference is like unlike a regular batch, we want to come to the center for the lecture. But you must be the center only twice a week for individual half an hour to 1 hour doubts and solving questions. Unfortunately, given the situation, this is what I'm able to offer you because had we been able to do the normal market kind of work last year, we would have had the integrated for integrated classes. But with the pandemic, unfortunately, our ground for what will not be able to do it at the same rate. Yes, yes, definitely. The only reason I did not send you the details was because now that was for the integrated program that we did. And we need to finalize the exact time for the set. I tell you that what is that and you can start attending the regular match from tomorrow itself because up to 10 July or 10 June class with the regular classes. So you can get a head start in this and then when we launch the non-integrated batch, we can switch over to that and then two classes take so for example, how those that is running right now is that the classes are 5 to 6 days old. 5 days on certain and 6 days on certain days. And that is there are lectures in the morning from 8 to 10 and then again from 11 to 1 and then again down session in the afternoon. But for receivers batch, integrated program right now is random because this is happening on all the lectures and down sessions are happening on. Now when we move from online to offline when the pandemic is over, then this will switch to instead of 5 to 6 days a week, 4 hour lectures. It will become 4 days a week, but lectures will be on 6 hours. The morning class will be 7:30 to 10:30, then 11 to 1, and 11 to 2, and then again in the afternoon from 2:30 to 4. 4 days a week will be that. 1 day a week will be going to college for the practical. 1 day a week will be test. That will be the curriculum for the integrated. Because for the non-integrated, what typically happens is students attend classes in the daytime. That is school in the daytime, and they come in the evening hours between 4 and 8 p.m. So that the class goes to maximum non-integrated. Intensity of the course is a little bit less, but then typically if your school curriculum is good, then that is compensated. So that the difference in our hybrid model is instead of coming to the center every day, they will come to classes. Non-integrated batch, the classes will be online for about 4 days a week, 4 hours, and another 2 or 3 days they can come to the center. No, sir. It will at least 3 hours. We have to cover all the subjects. What it takes. Yes. So that is what, sir. Me and my partner will work on the exact curriculum of this hybrid batch. But it will be the same as a regular non-integrated batch. The only difference is that the lecturing hours instead of being in the center, the lecturing hours will be online. Whereas for down sessions, they will come separately. Yes. Yes, I am. Yes. In fact, right. Sure, no problem. In fact, what I can do is like in fact later tonight I will go with my partners to discuss further about this. When we come up with a good curriculum tonight, I can have a good meeting with you and discuss it. I can have a biology faculty also present tonight because unfortunately, like I don't know that much about the biology syllabus. Physics, chemistry, maths, because I've been guiding students for daily and I've taken daily myself and my students. And apart from yes, but if she has any queries, yeah. Yes, okay, yes, definitely, sir. Yes, sir, definitely. So what you do is describe the strategy and by tomorrow I'll send you this in writing and document. Hopefully I'll have the fee structure also. And also in the meantime, sir, let's say if this batch is launched online classes with our teachers. But the only difference is that is in the morning hours, whereas in our regular class that in the evening hours, the duration of the classes, the faculty, everything is more or less the same. That will give us a good idea. How? Okay. Definitely. Definitely. Thank you so much. I'm sorry. Okay.
Okay, sorry guys, I had an important call to attend from a parent. Anyway, yeah, my mic was on. So let's see what are the concepts we can apply over here. Okay, so this is a system where when you look at when the particle comes and hits this here, no? Of course, up to then it is in free fall. Okay, so as it comes and hits, as far as the impulse is concerned, the particle applies an impulse like this. Okay, this is the collision impulse, let's say J, on the wedge, and the wedge applies an equal and opposite impulse J like this on the particle. But also, the ground will immediately respond by applying an impulse like this, let's say J prime. So it's not like the wedge is going to go in this direction, because the ground is supporting the wedge. So that's why we can say that on the overall system of the particle plus the wedge, we cannot conserve momentum because J prime is an external impulse. This is an external impulse on the system, which is the particle plus the wedge. Okay, but at the same time, J prime is vertical. It's a vertical impulse. So the horizontal component of momentum or the x component of momentum is still conserved. So we can see that horizontal impulse on the system is 0. So therefore, horizontal momentum of the system is conserved. So this becomes something important. Okay. So now once again, if we compare before and after impact, so just before impact, and just after impact. So just before impact, this has come and hit this with a velocity v0, let's say. So that v0 is how much? It's root 2 gh because it's free fall. So that when you calculate is 20 meters per second. Just after impact, it is given to us that this has a horizontal velocity of v1. So this will also have a horizontal velocity of v2. Okay. So from horizontal momentum conservation, you can see that initially before impact, horizontal momentum was 0 for the system. So after impact also it has to be 0. So minus small m v1 plus capital M v2 has to be 0. So m v1 has to be equal to m v2. That's our first equation. So this will tell us that v1 is equal to 5 v2 because it was given to us that the mass ratio is like that. Capital M was 5 times small m and h was equal to 20 meters. Okay, and theta was 53 degrees. This was the information I had given. Okay. But once again, one equation, two variables. So second equation where we are going to get from. So for that, you have to look at the particle. Now, what is happening to the particle alone? The particle is experiencing an impulse which is perpendicular to this surface. So this is the tangential axis. This is the normal axis. So additionally, what is happening on the particle? Okay, the impulse acting is normal. Okay, therefore, tangential component of momentum but for the particle, that's tangential component of particles momentum is conserved. Okay, so that will show us that before impact, the particle had a velocity v naught like this, where with respect to the tangential direction and normal direction, this angle was theta, and after impact, the particle is having a horizontal velocity v1, where this angle is theta. Okay, so tangential component of particles momentum before impact was mv naught sine theta. After impact is mv1 cos theta. So that's our second equation, and this gives us directly an answer that v1 is equal to v naught tan 53. So the speed of the particle increases to 4/3 times v naught after impact, and therefore v2 is 1/5 of this. So it is 3. Oh, just a minute, people. I have made a mistake with the question. Theta should be 37, not 53. So just make a correction here. We make theta as 37 degrees. Three by 4. Okay. So we got the first part. We got v1 and v2. Okay. Now we want the coefficient of restitution. Now we want to find out E. So coming back to this, the wedge was stationary initially, and the particle was hitting it with a velocity v naught like this, where with respect to the normal, this angle was theta. So what is the approach velocity of the particle? It is v naught cos theta. Okay. Whereas after the impact, you can see that the particle is going off like this, the wedge is going off like this. Okay. So with respect to the wedge, if you are in the wedge's frame, the relative velocity of the particle is like this. This is our v relative. This is the velocity of particle relative to wedge just after the impact. Okay, and again with the normal, this angle is theta. So from this we can see that our separation velocity will be this relative velocity, which is horizontal, its normal component. Okay, this is the normal component. Okay, so this should become v1 plus v2 sine theta. Okay, so that's our separation velocity. This was our approach velocity. So coefficient of restitution is separation upon approach. Okay. So the separation velocity is this relative horizontal velocity sine component. Approach was the vertically downwards velocity is horizontal component. So further this becomes v1 plus v2 sine 37 divided by v0 cos 37. So this is 3 by 4 plus 3 by 20 V naught into 3 by 5 divided by V naught into 4 by 5. Okay. So this is 3 by 4. If you take common, 1 plus 1 by 5 into overall 3 by 4. Okay. Still, I'm getting a strange value of coefficient of restitution. Getting it as 6 by 5, which is technically not possible because coefficient of restitution should be less than 1. Which means I have to adjust the ratio of masses or something over here. Oh, sorry, I made a mistake. This will not cancel. It's multiplying, so it's all right. So coefficient of restitution is becoming how much? It is becoming 9 by 16 into 6 by 5. That's less than 1. That's fine. So that's 27 by 40. So that's fine. There's no problem with that. It's a coefficient less than 1. So the question was all right. There's no problem with the data now. Okay, so anyhow, people, hope this question is clear. So sorry for delaying the end of the class, but just wanted to finish this before we conclude center of mass.
Okay, sir.
So that next time we can move on to rotation. Okay. So people, with this we conclude this chapter of center of mass or system of particles. As I said, a lot of questions in your module as well as HC Verma. So it might take you some more time to complete all questions and clear all the doubts and all that. So just continue doing the questions. We can keep aside some time for doubts in the next week also. But we will be starting with rotational mechanics in the very next lecture. Okay.
Yes, sir. Thank you, sir. Bye.
Okay, people. That's it for today then. All the best. Bye.
Thank you so much, sir.
Okay. Bye, people.